Welcome math group. Let's get some foundational work done for Unit 6. And Unit 6 we will be finishing up our work with finance and then also heading toward our work with statistics. Before we get there though, I'd like you to list some goals for yourself as we head toward the end of the semester, and then a little bit of feedback about the format that we use for Math 095 meeting before Math 115 so that we build that foundation in class and then use it right away. And some of the other sections meet after 115, kind of picking up the pieces and answering questions. So I'm wondering what you think you would have preferred and why that preference is the way it is. So just a little feedback for me. Here's some info from an earlier activity. I wanted us to just kind of examine the information from an online loan payment calculator. This is about a car loan. The amount that was borrowed from the lending institution is this loan amount right here, $7,208. The interest rate is 2.95%. And the loan period here is listed as months, so 36 months or 3 years. Okay. Our goal in this unit is to be able to take information like A, B, and C and find the monthly payment on our own with a formula, so without worrying about what a search engine would say or the loan payment calculator online. Here's the big formula for that. It is big and intimidating, but you are tough and you can handle it. So we need this. You probably want to put this down for your notes for quiz number 6 so that you have it ready. This is how we will find a monthly payment. PMT outside on the front, that stands for the monthly payment. A is the amount that we're going to be borrowing. The little r, lowercase r's, those are the interest rates, and those will go in as a decimal. The n's are just like the n's in compound interest. They will go in, I think we're only going to use monthly in here, so our n values will be 12. And then t, up here in this exponent as well, t is just like in compound interest also. It's the loan period in years. So there are some very similar things, but the formula got much more involved. So that's what all the component parts do. They're all listed down below as well. And then I just want us to make a list. For this particular scenario, let's make a list for the loan amount, the interest rate, the n value, and the t value. Well, I bubbled some of those a little bit earlier. The loan amount should be 7208. The R was 2.95%, and I wrote it as a decimal here for future reference. We're going to make monthly payments, so N will be 12. And the timing, we want it to be in years, so you would put 3 for that for right now. I think the next thing we're going to try to do is fill in the formula. So we're going to grab all of these pieces, going to grab this formula, and head over to the next screen. So there's the formula again. Here's what all of this stuff means again. And I tell you, okay, everybody keep breathing. Make a very careful attempt at filling in the components, and don't worry about evaluating it yet. Just put all of the component parts in and see how it should look. So I have it started. I have the 7208 for the loan amount already filled in. The interest rate was 0.0295, and that goes in a couple spots. The N was 12 because we want to make monthly payments, and that's very common out in the world. So the 12 gets repeated in the fraction that's in the numerator, in the fraction that's in the denominator, and then also in this exponent. And then the time in years, that was 3 years. So I have to get that to be multiplied by 3 up there. Well, that's not it. No, it doesn't want to do it there. Let me just use parentheses. That gets the job done. So I can see that the negative 12 and the 3 are both in the exponent right where they should be. So there's the fill in. We need to be able to evaluate this, and you have some options. You can use a handheld calculator, or you can use the Desmos Scientific Calculator. We'll talk about both. I really like the Desmos Scientific Calculator. You already know this about me, but the longer I use it, the more I fall in love with it. Let's scoot over to the next screen. There's the formula all filled in. You'll notice that the parentheses are a little bit different right here. It doesn't matter. They both mean exactly the same thing. If you are going to use a handheld calculator, this is the strategy I recommend. We're not going to do any rounding, no matter what we do. No rounding until the very last step of the problem. if we round in the middle of the problem once or twice, it throws the answers off. So save all of your rounding till the very last step. Handheld calculators, I say work out that exponent component first. It was negative 12 times 3. That's negative 36. Get that part tackled. And then for this particular formula, I'd like you to work on just the denominator part. 1 minus, parentheses, 1 plus, the funky fraction, close those parentheses and raise it to the negative 36. Let the answer just sit on your calculator. Don't write it down. Just let it sit there. What we would have done at that point is we would have taken care of everything down here. And so now we'd be left with leaving the answer right there, but we'd take 7208 times the numerator and then divide by that entire previous answer that you just found. So that's the instruction here. 7208 from the outside times the numerator and then divide by the previous answer. That's what that means. What do we get for the final result? Let's round it to the nearest penny and put a dollar sign on there. I am going to borrow this. Let me see if I can just copy this and put it into the Desmos scientific calculator with pasting. Paste. There's the answer over there on the right hand side. So maybe I can make it a little bigger. This is supposed to be a monthly payment. It's looking like it is $209.46. So let's remember that and go enter it. $209.46. That is supposed to be our monthly payment. So let's go back up here. Oh yeah, in the monthly payment from the online calculator, they said $209. I think they rounded to the nearest whole dollar. This online calculator is not official paperwork from a lending institution, so they can do that. Your actual lending institution will probably have a dollar and cent amount, just like we found with $209.46. Okay. So you have some options. Your handheld calculator, be very careful to not do any rounding in the middle. Use the previous answer feature. And if you're not sure where yours is, you can ask your favorite search engine for previous answer on, and then type in whatever your calculator style is. So I have a TI-30 that I sometimes use. I would type in previous answer on TI-30, and the internet will have answers for us. I'm absolutely certain of that. All right, so that's screen 5. I think that's all we needed to do there, and it was a lot, but we came up with the monthly payment of $209.46, and it's pretty darn close to the online loan payment calculator's number. So now let's try something start to finish. We have Trey that wants to purchase a building. The property is listed at $85,000 after a down payment of 20%. How much will Trey need to borrow? You've done these kinds of calculations before, but here they are again. 20% of $85,000 would be $17,000. And so that means that Trey is going to will want to borrow $68,000. If Trey gets a loan and agrees to pay it back in monthly payments over 15 years at 2.8%, what will the monthly payments be? By the way, right now, 2.8% is not very realistic. In 2021 and in 2020, this was a pretty realistic number. But right now, things have increased drastically. All right, so to fill in the payment formula, the loan amount is out front. Here's the interest rate in the two fractions. And we have 12 for the N. That shows up in 3 places, and then we have a 15-year loan. So there's the 15 up here in the exponent as well. So let's go get that amount. I don't know what the answer is yet, but I think I can copy it. And since I'm working in Desmos already, the copying and pasting goes pretty well. I think this one comes out to be $463.08. $463.08. There's our monthly payment. And then I ask for some follow-up information. If we want to pay this off completely, how much will we pay total over the life of the loan, and how much of that will be interest? You've seen things like this before. We just didn't have the ability to compute the monthly payment by hand. So Trey is going to pay for the down payment and all of the monthly payments. I've forgotten how much the down payment was. It was 17 grand. And then 15 years worth of monthly payments. So down payment is 17 grand. Here's 15 years worth of monthly payments. I just have to fill in that component. 463.08 is equal to, I didn't do that one yet, so maybe I can copy and paste this one also. We'll see. Oh, I bet it's not going to like that comma. We shall find out. Yeah, look angry. If I come along here and take out that 17, or the comma after the 17, this is how much we would be paying altogether, or Trey would be paying. So let's put that in. While we're right here, remember that if you're going to turn in work for me, like in the portfolio stuff, you want to have beautiful dollar signs on things, and you want to make this look like we conventionally do it in this country with 40 cents on the end rather than just 0.4. So this would be $100,354.40. By now, you know that when you get a loan, you end up paying more than whatever the agreed upon purchase price was. So $100,354-ish is greater than the $85,000. To find the total interest that's paid, take the total that we paid, subtract off the $85,000. That was the purchase price, and that will give us our interest paid. We need to subtract 85 grand. So if I use the previous answer feature, it'll say, yes, that thing, subtract 85,000. There's my interest amount right there, $15,354.40. I'm going to put a dollar sign on here. I like a comma. It helps me be able to read it a little bit easier. And then 40 cents. Make it look like 40 cents ought to look. So we found the payment for Trey's situation. We found the total amount that was paid. And then we were able to find the interest paid. So now let's try a different style of problem. It's often the case that if you can pay off a loan early, we'll save some money on that. You do want to check the fine print on your paperwork, but we have a formula for how could we find out how much we would need to pay off if we're going to pay something off early. It's not just as straightforward as saying, oh, take off these last few or sometimes a lot of monthly payments. There's, remember, each payment includes some interest with it, and so it's to our benefit to pay it off early, and we get a little bit different answer than what you might think. So new formula. It is also long. It does have similar components to the last formula, and you'll probably notice that the numerator and the denominator are reversed. They're flipped. So the payment, the R and the N all do exactly what you would expect them to, but there's a twist with the time. When we have a problem like this, T represents the number of years that are left on the loan. Not how many you started with, but how many are left. So find the payoff amount of the loan described below, and find the amount that we save by paying off the loan early. So after 10 years of monthly payments of this level, what's our payoff amount? Is this the same problem as before? Yeah, it is. It's related to Trey's situation. I didn't put that in there. All right, so Trey's going to pay for 10 years, and that means that they will have 5 years left to pay. Here's the formula. If we fill this in, our monthly payment goes on the front. The interest rate stays exactly the same as what it was. Oh, I forgot what it was. 2.8%. So 0.028 in 2 spots. We are making monthly payments still, so the ends are 12. And then the timing, we want the number of years that are left over on the loan. Well, it was a 15-year loan, and 10 years went by, so 15 minus 10 will give us 5 years that are left. So this is the thing we would need to compute. If you were going to do this on your handheld calculator, you would do the exponent first, and then do the entire numerator this time, using that negative 60. Then you would come outside to 463.08 times your previous answer, and then divided by this denominator down here. So if you are going to use a handheld calculator, I would highly encourage you to put an extra set of parentheses down here. I think I'm going to need this in a moment, so I'm going to copy it right now and then move over one screen. Ow. I thought I gave you a screen to answer that on. We're going to do the answer right here. So, equals, let me go ask Desmos calculator for some help. There's that. I copied it all in there. I'm just taking a quick double check and make sure things look like they're where they're supposed to be. The payoff amount would be approximately this, $25,899, and this 39 cents right here. I can't get it to highlight just the 39. We're going to call that 40. So math class rounding would say that's going to bump up to 40 cents. So I'm going to copy this part, but I'm going to fix the cents in just a moment. Scoot myself over. 39 was too low. Put a dollar sign on here. Oops. Dollar sign on here. There's our payoff amount. So that was the first part of the question. Find the payoff amount for the loan. Also find the amount that is saved by paying off the loan early. Let me give us a bunch of space. So if we had, or if Trey had continued to pay the monthly payments for those remaining 5 years, if they had continued to make those monthly payments each month for the remaining 5 years, they would have paid $463.08 monthly, so times 12, and then times 5. Well, let's go see how much that is. Grabbing that, asking for some calculator help. That's how much they would have paid, $27,784.80. Paste it here and clean it up. Dollar sign and a comma. There we go. That's how much they would have paid. By paying it off early, I'm going to say only, but it's still a lot of money. They only had to come up with $25,899.40. So continuing with the loan gets us a greater total than paying it off early. So the gap between those two is the amount that's saved. Let's go grab that. Oh, come on, slide over. This is the work that we would do. So we would have that minus oh, I have them in the wrong order. I have them backward. I would get a negative number here. It's not a huge deal. I wanted to put them in the other order. So let me put that one first. Minus. We'll change this to an equals sign. All right. So this is the total of all of the monthly payments had they occurred. This is the payoff amount for paying things off early. we need to do that subtraction. Popping back to a calculator, let's take that answer and we'll subtract off the $25,899.40. This is the amount that Trey saves by paying the loan off 5 years early. $1,885.40. And again, if this is your loan, you do need to read the fine print on your loan about whether you can actually cash things out early or not. But often, if you can cash them out early, it is to your benefit to do so. You'll get to save yourself some money that way. So in this case, about $1,900 Trey got to save by paying things off 5 years early. All right. So we had a formula already today for the payment, the monthly payment. We have a formula for the payoff amount, and these are all about loans. We have one more formula for the finance component of things, and this one is a bit more uplifting. This one lets us figure out if we made regular, equal monthly payments into accounts over a long time, and we didn't make any withdrawals, and those earned interest as they went along, what would the total value of the account be at the end? This is the future value of many, many, many equal payments over time. So we get one last formula. There's FV for future value. Payment is exactly what you would think it would be. And the R's and the N's and the T's all behave exactly the same way that they have been. We just have to get everything in the right spots. So let's pretend we have Grandma Big Bucks has a new grandbaby. The grandma decides that she will put in $50 every month for 18 years in an account that pays 4.6%. Not ever going to take any money out, going to just let everything sit there and gain interest. She's going to give that money to the grandkid when they head off to the college they want to go to or whatever they're going to do when they're 18. I'd like to know how much will be in the account at the end and how much of that will be interest. So let's fill in this formula. She's putting in $50 every month. 4.6% interest is 0.046 in its decimal form. Let's put those where they go. These are monthly payments, so the ends are 12, like they have been the rest of the time today. And then the timing here is 18 years. No, not that one. It's not liking that so much today. 12 times 18. All right. So there's the formula all filled in. If you're going to do this on your handheld calculator, again, do 12 times 18 first. 12 times 18, I forget what that is. 216. And then you will do the entire numerator. And then take that numerator and multiply by the outside payment, and then divide by the denominator. And if you are using a handheld calculator, you'll want to use that extra set of parentheses around the denominator. Okay. The calculator isn't as smart as you are. It doesn't always know what we mean. If you know all of this, we can head off to the Desmos Scientific Calculator. This time let me pretend like we don't have the copy-paste feature. So this was supposed to be $50, and then we have a big fraction. So I get the parentheses open, I get the big fraction happening. I have to grab a little bit more information. My interest rates were 0.046, and it's 18 years. Okay, so up here, we can open another set of parentheses, 1 plus. We need another fraction, so hit that division sign or the fraction bar, 0.046 over 12. Close that set of parentheses. You can use this a to the b feature to get an exponent. We need 12 by 18 up there. And then I think the next part is -1, but I'm going to jump back and double check. Yeah, it is. You can tell I don't have these memorized. I don't use this one enough to have it memorized. Down below, we get a copy of that fraction. So we need another fraction set up, 0.046. Divided by 12. And we can close this set of parentheses if we want to. So payment out front, interest rate filled in, monthly filled in, the years that go by are filled in. This is coming up with $16,762.39. Gonna grab that. Gonna go put it in my answer area. Future value equals $, maybe a comma for some clarity there. Let me give us some space. And if you are a copy paste person, just to prove, we'll get the same thing twice. You can copy it, head over here, paste it, same answer. If you have something like this set up in the Desmos graphing calculator, you can just come in and edit it for your new situation. That's kind of nice too. All right, what else were we supposed to do? How much is in the account at the end? So this is the at the end. The interest will be the gap between the amount that we have at the end and the amount that the grandmother put in there. So interest is going to be equal to, let me grab this, minus, she made monthly payments for 18 years and the payments were $50 each. So you can do this in chunks if you want to, or you can do it exactly like this without the comma, all in one chunk. I know, it's all angry with its orange exclamation point. Here's the amount of interest. So by Grandma Big Bucks doing this, the grandchild will get all of the grandmother's payments plus almost $6,000 in interest. And depending on the type of an account it is, like if it's an account for education purposes, like saving for college, sometimes you pay a different tax rate on that, or maybe no tax at all. But often with interest, we end up paying taxes on it. It's just a feature of how things work in this country. So just be aware. We're not going to do the calculation for that, but just be aware that it is often the case that you'll pay interest, or sorry, you'll pay taxes on the interest that you earn. I think this one is done. How much is in the account at the end and how much is interest? I think it looks good. And then I switch this up. That was the end of finance stuff. You get 3 new finance formulas, 3 new finance scenarios. The main key is going to be figuring out which one to use when. When we head towards statistics, I think this is a timely example, finding a grade point average. To find a grade point average, we need to know the classes a person is taking. So I've listed math something and fundamental something in WPE. We need to know how many credits each course is worth, and we need to know the grade that the person is earning. To find a grade point average, we need to find something called the quality points. I already have them filled in here. But what we end up doing for that is we take the number of credits times the grade in each case. So if we were hanging out here, we would have had 3 times 3.5, and then we get a big old equals, and it should be equal to the 10.5. So we make all of those products. If you do 4 times 1, you'll get 4. I'd actually really like the answer to be up here and not the calculation, so give me a second. There we go. 4 times 1 is 4. 2 times 2.5 is 5. So we find all of the quality point components for this person's scenario. We're going to find the total of all of the quality points also, so we'll add them together. There's, let's see, 4 and 5 is 9, plus another 10.5, 19.5. And we also need to know the total number of credits the person is taking, so 7, 8, and 9 of them. The grade point average is computed by dividing the total of the quality points by the total number of credits. And at an institution like KVCC, where we have a 4-point scale, the answer needs to be between 0 and 4 included. We could have a 0 GPA, though I don't want that for you, and you could have a 4.0 GPA. Let's see what this one turns out to be. We should do 19.5 and divide that by 9 and quick calculation here. Handheld calculator helping that time. Mine is telling me 2.1666666 forever and ever. And the instructions said to round to the nearest hundredth if we needed to, if it didn't come up very nice. And it doesn't come up very nice in terms of the decimal component. When we round it to the nearest hundredth, we'll get 2.17 for the GPA. This number does need to be between 0 and 4, and it is. And we can even be more specific. For this particular student, they have a low score of 1.0 and a high score of 3.5, and so their GPA needs to be between those two. If it's outside of that range, then we need to back up and find out what's wrong. So finding grade point averages is on our agenda for this unit. We should also be able to read some plots and do some interpreting. This is called a stem and leaf plot, and we'll just kind of get used to it to start with. Let's see, can I make this bigger? I can. I wanted to use it, but let me erase this. I don't want it there. Grab this and move it up. All right. So with a stem and leaf plot, what a person is trying to do by using it is to organize all of the data points in a way that they go in order, and we can kind of see where the pileups of data points are. So you'll notice that the row here that has the 2 on the front, on the left-hand side, there's a lot of things in that row, but then there's nothing in the row that starts with the 3 for the stem. So stem and leaf plots can give us an idea of where our data points are bunched up, but we should also be able to say some other things, like what the heck does it all mean? So the key down here tells us that 4 for the stem and 7 for the leaf means 47. And I've told you in the instructions that that really means 47 years old in this scenario. So we have people that are going to an event at the museum. Somebody has asked for their ages and recorded them and then organized this. This top row means that we had someone who was 12 that visited, and a 14-year-old and an 18-year-old. So if you wrote out the list, you would have all of those. Usually we don't write out the whole list. This second row would tell us we had a 22-year-old and another 22-year-old, and then a 23-year-old, a 25-year-old, a 25-year-old, and a 28-year-old. We have nobody in their 30s, and then we have 45-year-old, 47-year-old, and a 48-year-old that visited. So we know what the data points are, even though they're not all listed explicitly. We can answer some questions. Let's see, the youngest person at the event was 12. That's true. We started up here with the 12, and they go in order all the way up to 48. The oldest person was 48. That is also true. There are no people in their 30s at this event. The row that was for the 30-year-olds is empty except for its stem. There's nothing listed over here. There were 16 people at the event altogether. Well, let's see. We know the people from the leaves. So we would have had 3 people that were 12, 14, and 18. There's 3 people there. So 4, 5, 6, 7, 8, 9, 10, 11, 12. This isn't true. It should be 12. We only have 12 leaves in this case. So don't check that bottom one, just the other 3. I think this is the same stem and leaf plot. But now I'm looking for a mean, a median, and a mode. I have some stuff taken care of over here, but just hang with me for a second. I'm getting things set up. The mean, it's what some of us call the average. We kind of use those interchangeably, even though average can mean like a grade point average, which is different than a mean. For this mean, we are trying to indicate that we want to take the total of all of the ages and then divide by the 12 people that were present. The median is the middle entry. So if we have 12 people present, the 6th and 7th entries are forming our middle, and we need to split the difference on those. We'll see that in a second. And then the mode is the most frequent entry, or the most frequent age. Sometimes there's not any mode at all, and sometimes there's more than one. But let's see what happens with these. For the mean, we'd have to add up all of the ages, and that's a bit of a nuisance. I don't like to do them all at one time. I like to do them in little chunks. So if I did 12 plus 14 plus 18, I get 44. And then 22 plus 22 plus 23 plus 25 plus 25 plus 28 gave me 145. And then 45 plus 47 plus 48 gave me 140. So I use that kind of format with a stem and leaf plot to get going on a mean. That way I'm not doing as much typing at one time and potentially losing a digit, having a little error like that that's going to throw things off. So once I have those three totals, I can put them all together. And let me make a fraction here. 44 plus 145 plus 140. I think it's 325, but let me double check. 44 plus 145 plus 140. Oh, I was off by a little bit. Yeah, I forgot to add the 4 and the 5 together in the units. It's 329 for the total up there. And then we had 12 people who came. So 329 divided by 12 is 27.41666666 forever. Let's call this 27.42. And I'd like to be able to put a little label outside my box. Yeah, you know, that was supposed to be up here, but it's not going to fit. So 27.42 years old is the mean, and that should be between the low end and the high end. The low end was 12, the high end was 48, and we're in between there. It's not a perfect double check, but it at least is reasonable. For the median, the middle entry, sometimes I see students do this. I kind of like this too when the lists are short. Oh no, I lost my other info. You have it, you can back it up in the video, but I lost it, so we'll hope that I don't need it too badly. For the median, sometimes students will come along and they will go slashing on the list. Cross off the first one and its partner at the last. Second one and its partner on the end. Third one and its partner on the end. And they keep slashing, slash, slash, from the low end to the high end until they either get to just one entry in the middle or they end up at 2 entries in the middle. If there's just one exactly in the middle, then we're good. We use that for the median. But things get more interesting when we have 2 items in the middle. Our items are 23 and 25, and we want the mean of those. Well, probably you're thinking, oh, halfway between 23 and 25 is 24. That's true. But if you're unsure, if the numbers are strange and they have weird decimals and it's hard to figure out that middle part, then just use the average. So the mean of the 6th and the 7th would have been 23 plus 25, and then divide by 2, which is 24 years old. So that's one idea. Also, if we had 12 entries, then we know that 12 divided by 2 is 6. 1, 2, 3, 4, 5, 6. So right there should split us into a lower half of the data and an upper half. 1, 2, 3, 4, 5, 6. And we know we need to be exactly in between 23 and 25 using that kind of idea as well. Phew. All right, there's the median. The mode, we need something that repeats, if anything. Let me change colors. When I look through here, it kind of seems like the 8s are repeating. I can see them in the leaves, but this goes with 18, and this one goes with 28, and this one goes with 48. So those are not repeated data points. So let's not use those. Let's look within each row. Are there any repeats within each row? Nothing repeats here, 12, 14, 18, no repeats. But we have, these are repeats. 22 is repeating. And then these 5s, those are repeating. We get 2 people who were age 22 and 2 people who were age 25. And that's the most repeated stuff that we have. Those are our modes. We get 2 of them. 22 years old and 25 years old. You can have more than one mode, you can have exactly one mode, and you can have no mode if nothing repeats. All right, I'd like you to be able to read a stem and leaf plot and do some interpretation like this, like how many data points are there? What's the mean of all of those? Those kinds of things that I've asked in the last 2 screens. I'd like you to be able to do that. We will also work with frequency tables. That's what this thing is. This table tells us that 5 students received 0 parking tickets, 2 students received 1, and 3 students received 2 parking tickets each. You got some true and false going on here. This statement says, oh, so much blue. 1 student reported getting 2 parking tickets this semester. 2 parking tickets, that goes with 3 students. I'm not liking the phrasing of my own question. I think we want it to be false, but a better phrasing would have been exactly 1 student reported getting 2 parking tickets this semester. My theme was false, but I probably should have the word exactly on the front of that. Let's try out this other one, see if that one's going to be a nuisance. This one says 3 students reported getting 2 parking tickets this semester. 2 parking tickets from the lower row. Oh yeah, it is 3. This one is true. That's kind of how to read it. Let's go use it for some other things. I think this is the exact same table. For this group of students in this table, how many students were surveyed? This one's pretty nice. I like this one because I can see, oh, we had 5 students doing something, 2 students doing something, 3 students doing something, and that means I just need to add those 3 together. Not just, but that's what we would do. 5 plus 2 plus 3. So I think it's 10 students that were surveyed. I already left a hint down here for myself. Letter B has to do with products. How can we figure out how many parking tickets total were received by this group? Like if we had them all present and they had their paper parking tickets in front of them, how many of those tickets would we be seeing? Well, 5 of those people had no parking tickets. We're not going to get any to show up from them. 2 people had exactly 1 parking ticket each. So 2 times 1 is 2 tickets. And then 3 people had 2 tickets each. So first person has 2, second person has 2, third person has 2. If you do 3 times 2, you'll get 6. So we'd have no tickets from the first group, 2 tickets from the second group, and 6 tickets from the third group. Products. 5 by 0. Should be a plus. It was 2 by 1. And 3 by 2. 0, 2, 6, 8 tickets. And then finally, what's the average number of parking tickets per student? Well, this means this is a different kind of use of the average. We would want to have the total parking tickets and then divide by the total number of students. So we have 8 tickets altogether. And if we divide by 10 students altogether, this would give us 0.8 tickets per student on average. I do not think that it is physically possible to get 0.8 of a parking ticket. This is a mathematical measure of the center of things. So mathematically speaking, we can talk about having 0.8 of a ticket as a measure of center. But it's not physically possible, I don't think. And as I say that, I'm envisioning people ripping part of their ticket off of the stub somehow. I don't know. This one is a frequency table, and we can answer questions about how many students or how many people were surveyed, how many of the other feature happened, and then we can talk about averages for that as well. All right, here's a student's scores from their biology class. That's their test grades. These are supposed to be percentages. It says in the instructions, even though the percentages aren't on the list. We need to find the mean. And the mean is found by adding up all of the test scores and then dividing by the number that we have. So I did this one ahead of time. Add those all together, 85, 70, 82, 60, and 90. I got 387. I need to divide that by 5 test scores. I got 77.4%. I did put the percent sign on the answer because it was a final answer. It does need to be between the lowest test score and the highest test score. The lowest test score, I think, was 60, and the highest was 90. And my answer for the average is between those two. That's pretty good news. If it's beyond that range, then we need to go back and find out what the error is. Find the median. The median is the middle score if we order them from least to greatest or greatest to least. So I need to take those scores and get them in order. I'm going to use a little text box to do it over here. Let's see. I think the lowest score is 60. We just talked about that a moment ago. Give myself a couple spaces. And then 70. And then 60, 70. How about 82? And then 85. It likes to give me a little decimal point there. And then 90. I'm double checking to make sure I typed them correctly. And there are 5 of them. All right. So the median is the middle. Well, if you take 5 scores and divide by 2, you'll get 2.5. And that means 2.5, bump it up to the next whole number. That would mean the third entry should get the job done. 1, 2, third entry is right here. So it's looking like it should be 82%. If you are a slash type of person, you will slash through the 60 and the 90. Those are partners. The 70 and the 85 are partners. And then you'll notice this time we have exactly one item left over in the middle of the set, and it's 82. So that would be our median. There's a variety of ways to get there, but you do want to have things organized from least to greatest or greatest to least. 82% is the median. I bet this is the last one. Find the mode. Oh no, there's one more after that. The mode is the most frequently occurring entry, but we don't have any test scores that repeat. So there is no mode. No mode. Because no score is repeated. That's actually one of my favorite answers because you don't have to do a whole lot with it. Just like there isn't one, nothing repeats. We're good. Last one, range of the test scores. We subtract the least score from the greatest score. So in our case, the range should be, I think the high score was 90, the low score was 60, and so 30% is our range. I think I would actually call this 30 percentage points for a range so that it sounds a little bit more specific and maybe more accurate, but for our purposes, 30% will get the job done. I'm going to go double check on the 90 and 60. Yep, 90 was the high, 60 was the low. We're good. We are in charge of mean, median, mode, and range for some basic statistics to start with. We're in charge of stem and leaf plots, and we'll also work a little bit with box and whisker plot. This one is called a box and whisker plot. There's a big box chunk here in the center, and then these edges over here are supposed to be the whiskers. Okay, so box and whisker plot. Let's say that this comes from a group of people who has been surveyed about the number of paid sick days that they're awarded each year at their job. It's organized in a box and whisker plot, and this is done to show where the data points are very far spread out and where they're tightly packed together. So you'll notice that this whisker over here is really long compared to this first left-hand chunk of the box. That means that for the people that we surveyed, things are really far spread apart between 0 and 4, but things are really tightly packed together between 4 and 5. Okay, so that's why we use something like this. It shows dispersion. If you had to guess, according to the plot, what is the minimum number of paid sick days that people reported in this survey? Well, the minimum is labeled over here. It's looking like 0. And that's kind of sad. Like, ugh, all right. Maximum reported in this survey. That's way over on the other end of things. we can pull it off of the scale. Looks like 10 sick days was the high end of what was reported. Minimum and maximum, got those. I was looking for another question. Usually I have more to ask. Oh, I get to recycle it over here. All right, so this Q1 right here, it has some other names. It's also called the first quartile or the lower quartile or the 25th percentile. And what it means is that between the minimum and Q1, like from Q1 over to the left, we are capturing 25% of the responses. So 25% of the people earned four paid sick days or fewer. Q2 happens to also be the median. There's Q2 right there. It is the median. If we measure from here over to the left, 50% of the survey responses would have had 5 sick days or fewer. So the median cuts things in half. That's where that 50% comes from. Q2 is also called the second quartile, the median, the 50th percentile. And then we have a Q3 as well. And I think I asked you to kind of use some pattern recognition to talk about how we would describe this. So for Q3, box and whisker plot chunks things up into sets of 25%. So Q3, this is going to be an upper quartile or the 75th percentile or the third quartile. And we would have gotten 25% from the first whisker, 25% from the first part of the box, and another 25% from the second part of the box. So if we're talking about 7 sick days or fewer, that would mean that 75% of the responses said 7 sick days or fewer. So let me go put this all in the box. It's called the third quartile, also the upper quartile, and the 75th percentile. And 75% of the people earned 7 sick days each year or fewer. And like always, I encourage you to make mistakes on these so that they are all spiffed up by the time we get to the quiz. I think box and whisker plots actually spill over a little bit into Unit 7, but don't quote me on that just yet. All right. I think the next part is just kind of a check-in, a little robot-y check-in for you. All right. As always, well, we're not going to end over there. Let's end over here. As always, if you have questions, please reach out. Keep hanging in there, little bits at a time.